test. All right, guys, let me catch up to you.
That's a good investment.
Yay. All right. So probabilities have to be between what two things? What's the lowest a probability can be? Zero. Because zero means it ain't going to happen. What would negative mean? So not going to happen. I don't know. And what's the biggest it could be? 100%, right? If there's a 120% chance of rain, I don't know what is that giant raindrops? Is it raining like on top of itself? I don't know. So make sure when you do this, your answer is not bigger than 1 as a decimal, right? 100% is 1, or smaller than 0, obviously. So attends Grossmont. How many students attend Grossmont in this sample? 126 out of? Which is?
0.7159.
7?
0.7159.
159? 9, okay. All right, how we know so far?
Solid.
I didn't see anybody doing this, but these don't build on each other. Part B is its own question. What's the probability I pick somebody who's a business major? 92 out of 176. In fact, the only question in this whole thing that's not going to have 176 in the bottom is the given one, part E. That's the only time I could throw some people out and change the denominator is if they give me more information. What is 92 out of 176? 5227? All right. So then this guy, you can either do the equation, which is basically you add computer science people to Grossmont people, and then you subtract the number. All right. Watch, how many Grossmont people are there? 126. How many computer science majors have I not counted in that number yet? 11. 126 plus 11, 137 out of 176. Right? So either way you do it, if you did the minus thing, you should have ended up there still, right? So if I can count all the situations, I don't have to use a formula. I could do whatever makes sense in that situation. I like it. There's a problem on here that we have to use a formula for, so we'll get there. So what did I just say? 126 plus 11, 137, 176, and whatever that is. 7784?
Cool.
Yeah?
Yep.
Okay. Now look, D is an and question. My answer should be smaller than either one of those would be, because they have to do both. So how many students are math majors and Cuyamaca students? Only 2 out of 176. Because this could still be anybody. I didn't tell you anything about them. I don't know what the hell they are. So 2 do these 2 things out of 176. Whatever. What is it?
0.0142.
Who? What?
0.0142.
Like that? Sorry. I love crowdsourcing my work. All right, here's the only thing now. So what goes in the bottom?
73.
Because that was how many computer science. So the given piece goes on the bottom out of 73 people, because they know they're a computer science major. How many go to Grossmont? 62. Holy crap. And what's that?
0.8493.
0.8493? Okay, I like it. So are being a Grossmont student and a computer science major, are those independent? Well, what I have to check is the probability of Grossmont the same as the probability of Grossmont given computer science? Or I could check the probability of computer science, is that the same as Holy shit and a half. I could write correctly. And then everything would be so much easier. I could check if Grossman's probability changes there, or I could check if computer science's probability changes there. Now, of course, which one have I already got the work done for? This one, yeah. But it doesn't matter which way. If one affects the other one, then it will go the other way too. So it doesn't matter which one I check. And I will pretty much always, you will already have done the work to answer that question. You just have to go find it. So in this case, what parts are we comparing? Screw that. A, because that's this guy,
And E.
0.7159, and 0.84, that's Grossman given computer science. Those are not equal. Therefore, these are dependent. I've run out of room because of all my craziness. Dependent. Bah! Be a better student than me. All right. Sweet. Do you see that? Maybe? Okay. All right. Yes?
Could you also compare the probability of Grossmont students and then compare the probability of Grossmont and CS?
No.
No.
Nope. Because that still doesn't tell me how they interact. The only one that tells me how they interact, if they do, is the given. That's where one thing happened, and does it affect the other thing? That's why I have to check the given in an independent question.
Okay.
Maybe. All right. So let me build up what we need for this next. The first part of the next problem you should be able to do, right? Let's do it. And then the second part is like, what the shit? So I think this is just me dreaming about it. I want to shove all these people into a freaking, well, you know, I won't finish that sentence, but a Honda house would do. If you pick one person at random from the house, how many people are there in that house?
21.
Yeah, 21. What's the probability that that person I pick is a Democrat? 7 out of 21, which of course is beautiful 1/3. So 33.33%. Or it would be if I was somebody who could write. Probably that person is a Republican. 12 out of 21. Okay. All right, so those two I could do. Can you see this next part definitely has parts to it that we don't know what to do with yet. So let's talk about that. Because we can do picking one person, but the minute I pick multiple things, how does the probability kind of accumulate at the end? All right. Oh my God. All right. Beep. There we go, Jeff. All right. So this is kind of cool. Let me see. Yeah, I think I want to do that. Let me keep that up there. Do you notice what's formula have we not done yet? We have or, we have given, we need and, right? And we haven't done a problem yet that we have to know a formula for it, because and in a table is easy. It's just where the two things intersect. But again, I'm not always going to give you a table. I'm going to have a formula eventually. And that is actually what these, do you see? That's a probability of some event and another event between two things happening. We don't have the capability to do that yet. So if we can develop a formula for and, we can do it. All right. So I want to first develop a little intuitive sense. Let me do the non-goofy example first, so I don't like totally lose you, and then I'll do a goofy example. The non-goofy example is very not goofy. It sucks that I have to say this phrase, but the first time that the Challenger, that the space shuttle blew up, was in 1986. I was in English class. I was sitting in the first row, fourth student back, when I found out. And I remember that. There's been events in your life maybe that you remember where you were, right? It could be personal events, it could be big events. In fact, some of you guys might not even be alive, but like 2001, 9/11, all that kind of shit, right? I was and still am obviously a geek. And I was all about the space shuttle, all about the shuttle program, all about space. And I lived in Florida, so we used to go out and watch the shuttle take off. For some reason that day we didn't. So I didn't get the news until later in the day when I was in English class. The news came through and the teacher told us, oh yeah, the shuttle blew up early on, and I just started crying, like the little geek that I was. And of course, people lost their lives, but it was a huge setback to the space program. Now, do you guys have any idea why that first shuttle exploded?
The temperature?
Yes, had to do with the temperature. It was a very, very cold morning. And there were these things.
It's a gasket or an O-ring, right?
O-rings, look at that, kick-ass. So on the gas line, there were these O-rings, which are basically a type of valve that only allow the gas to flow in one direction, which sounds like something you want. You only want that sucker flowing in one direction, right? You with me? If they flow the other way, things happen like what did happen. Normally, all right, now watch. Why would they want multiple O-rings? Why would you want multiple locks on your door if you live in a worse part of town? To make the probability somebody gets in small. I like it. Right? And why would you set multiple alarms if there was an incredibly important interview you had the next morning? To make the probability you miss the interview less. I like it. So let's say, just to make some easier numbers to work with, let's say that these both have a 1% chance of failing. Right? Thankfully it was less than that, but on the morning it was so cold, they didn't take into account that the O-rings viability would go way down. So the probability they failed went way up. And that's exactly what happened. Right? The gas flowed the wrong way, boom. Everybody kind of with me a little bit? I'm not going to quiz you on the space shuttle. Don't freak out. I'm not going to quiz you on O-rings. It's just an example. All right? So so what's the only chance? If I had two O-rings, what's the only way that gas would flow the wrong way? Is if both. The probability that this guy and that guy failed. Fail one and fail two. Is that all right? If and worked the same way or did, and I added them, now I have a 2% chance. That doesn't make any sense. That doesn't go along with the whole idea. I want to decrease the probability, right? So now watch this. How often will this one cut out? Not work. 1% of the time. Of those times, of the times that he fails, how often will he also fail? 1% of those times. Does anyone know what of means in math? Thank you. Multiplication. So this would be 1% of 1%, which is 0.01 times 0.01. Which is what? 1, 2, 3, 4, right? So that's, a 0.01% chance. So if they put in another O-ring, now it's going to take it back 2 more decimal places. So can I ever make the probability of something like that 0? No. But I can make it very, very, very small, right? You guys semi with me? Exactly the same idea as putting multiple locks on your door. All right, you can pick this kind of lock, but can you pick this kind of lock? Yes? Oh shit, can you pick this kind of lock? Yeah, oh shit, can you pick this kind of lock? All right, so you just put multiple locks on there. So at least it takes them too long, right? Here's somebody out there, hey, and then maybe the police get there in time. All right, so the main thing I want you to realize here, and seems to mean multiply. And the only kind of numbers that when you multiply them, they get smaller are numbers between 0 and 1. So when I multiply two probabilities, the result does get smaller. And what do we say about and? And should always make the probability smaller because it's more restrictive. You got to do both. Here's a silly example. All right. This is really something. So let's say I want to join a fraternity, and they have some non-news making hazing I got to go through, right? So nobody's going to pass by. So I'm going to walk down this long hallway. You with me? Everybody with me? I got to walk down this long hallway. Every 3 steps I take, somebody slaps me on this cheek. And every 5th step I take, they slap me on this cheek, right? So how many steps when will they hit me on this cheek and this cheek? No.
Every 15.
15. 3 times 5, right? Think about it. Every third step here, every fifth step here is going to have to be the common denominator. Is when they're going to actually hit me on both. So to be honest, if you look too much into the example, you'll see where it kind of fails. But I like this goofiness. It still means multiply. There's a 1/3 chance I get hit on this cheek. 1/5 chance I get hit on this cheek. So it's probably get hit on both cheeks at once. This cheek and that cheek, 1/3 times 1/5, 1/15, every 15 steps. And like I said though, if you go, don't look too deep into that because it quickly falls apart. But it's a decent little goofy example of why it's multiply. Now, sort of with me. And apparently wants to multiply things for many reasons. Here's the ultimate. Here's the proof. Neither one of those is proof of shit. Right? Two very specific examples. Here's the proof. What's the formula for this? Right, there it is. Make this a little less. Whoa. Oh yeah. Get higher for that. Do you see the thing we're trying to talk about right now in this equation? How do I solve for this? Won't I create a formula then? If I solve for it, right? No? How do I solve for it? It's very simple. Multiply by PB, right? Multiply by peanut butter. Get in there. Plop, so the probability of A and B equals the probability of B times the probability of A given B. And how does that match up with our two examples? And means multiply. What's interesting, what I want you to notice is, I don't want to say this. On that cold morning, was the probability of both of these still 1%? So if this one does fail, could the probability this one also fails be higher than, yes, because there's maybe something that made this guy fail that will make this guy also fail. That's why there's a given here. Given that the first dude failed, I multiplied by the probability that the second dude fails in that case. Maybe.
So it's really just A times B.
In a sense. So watch. If A and B are independent, then what's this formula become? Probably a B times, if they're independent, what's true about this? It equals PA. So the only time you can just directly multiply two probabilities to get there and is if those are independent events. And again, we are deep in the section of probability that does not make immediate sense. We have to set up based on the basic idea of probability, which is based on survival, which is why if we always go back to that, we should make it make sense. So we've done a lot of shit on top. This is after we've done a lot of other shit. But that's the beauty of mathematics. Once I set up something I know is true, if I do algebra stuff to it, the truth of it stays the same. That's the big thing to learn from algebra. So I got an equation we set up because based on something we did. If I solve it for a piece of it, it still is a true equation. All right, now, this is all nice for concept, Jeff. How the shit do you do this stuff? All right, here we go. Let me give you some examples. Let me add this formula over here. And let me see if you guys can handle this. Let me write it twice. It works both ways. Because what's the probability B given A? What's the only difference? The bottom would be A. And then I want to multiply by A. So probably maybe it's the same thing either way. You got to trust me a little bit. Give me a minute. And then once we do some problems that use this practically, it'll make a little more sense, is the hope. And then we'll be doing this. I'm going to take this away. Is anybody that doesn't know the basics of cards? Do you know how many suits there are in a deck of cards? Huh? No, that's how many cards. How many suits? 4 suits. So you guys, I'm not asking if you could play, you know, no holes, whatever shit, poker, you know. Right? You with me? No, we're not gonna. I know the math, but I don't have the poker face for that. Right? We played for Oreos, and I'm like, I didn't need any freaking Oreos because they were all gone. All right. So, let me see what you guys think. How many kings are there in a deck of cards? 4. So, watch this. If I pick one card from a deck of cards, what's the probability I get a king? Yeah, 452. Is that cool? Which is 1 out of 13 and whatever the shit that is. Well, now watch this. It's kind of cool. Little side note. If I reduce that, I get 1 out of 13. Why does that make sense? There's 4 suits, 52 cards. How many cards for every suit? How many hearts are there? How many diamonds? 13. Out of every 13 cards, how many kings are there? 1. So when I reduce a probability, very often that has its own physical meaning. That's just a side note. And what is that, real quick? What's 1 divided by 13? 7, so 0.0.
0.0769.
Thank you. Save me for myself. Now let me ask you this. So this is pick one card, right? So what if I now pick 2 cards? And I've got to designate how I'm going to do this. Pick 2 cards with replacement. Meaning I pick a card, I look at it, and then I put it back in. And then I pick the next card. So can I get the same card I picked in the first time? Yes, because it's back in the deck. With replacement. What's the probability I get a king and then another king? So I look at this as like a hangman game, because I'm weird. 2 things I got going on here, right? So I got 2 spots. What goes in the middle? What operation? Well, what's and? Times. What's the probability the first one's a king? 4 out of 52, or 1 out of 13, even better. I put that card back in. Actually, let me keep it 4 out of 52, just for now. Put the card back in. What's probably the next one I get as a king? Still 4 out of 52. All right, nothing major there, right? Nothing to see here. And that's 1 out of 169, whatever shit that is. Let's see. 0.006. 005.
0.0059.
Yeah, oh, okay. Well, that wasn't bad, right? That's pretty good. It's my 1 skill. So, now, what if I were to pick without replacement? And still, what's probably get a king and then another king? So again, I got hangman game, 2 things. I could have had king and then another king and then another king, and then I would have had 3 spots. But what would they still all be separated by? Times, because it's and. What's probably the first one's a king? That's crazy. And then I feed it to my little brother. Explains a little bit about, sorry Jim. You'll recover. Right, that card's gone. So what's probably the next one's a king? 3 out of 51. You guess. So if I had another one, it would be 2 out of 50. I had another king, right? I just keep going. So the idea of and doesn't matter how many things, I just keep adding another spot on. With replacement, the probabilities don't change. Without replacement, they might change. And then whatever the hell that is. I don't know. I might never find out. Anybody got that?
Zero, 0.045.
0.0045. Cool. And of course, do you see how much smaller the probability is there? Because I lost a king on that second thing, and so my overall probability went way down. Gotta get 2 kings. Okay, maybe. No? Not at all. Shit. Let's do one more. What if I pick 2 cards without replacement? What's probably it's an ace and then an 8.
So for the bottom part, it's 4 over 52 times 3 over 51. So do you have to just look up for the same denominator and then just do the whole, or what is it you did right there?
All right, now watch. I'm glad you asked the question. I picked a card here, right? There's a 4 out of 52 chance that card's a king, and then I threw it away. How many cards are there now? 51. And how many kings are there? 3.
But then how do you got, like, do you have to look up for the same denominator or just multiply?
Oh, I see what you mean. All right, you ready? Like terms is only required if I'm adding, subtracting. Can you add x plus x squared? No. Let me just help you out, right? Just in case some of you guys think. But what's x times x squared? X cubed. So you see how multiplication is nowhere near as restrictive as addition and subtraction. So why do we have like denominators? Well, I have to have like terms to add or subtract. So 1/5 plus 2/5, that's like terms. One of these plus 2 more of these is 3 of those. But if I have 1/5 plus 2/15, oh shit, now I'm trying to add 1 of these plus 2 of those. So I make like denominators because then that makes them like terms. So that's all like denominators are, is just making things like terms. Here I'm multiplying. I don't give a shit about like terms. In fact, I'm trying to reduce, right, when I'm multiplying. So please, dear God, don't make the bottoms the same. Right? You just multiply that stuff. Can't like it. In your calculator, you put 4 divided by 52 times 3 divided by, put the whole damn thing in there. Don't round this and then round this and then multiply, because then your answer is going to be way off.
So for the without replacement, we automatically assume that they potentially got king.
Oh, beautiful. Okay. I love and hate that you're asking this question. This is all about, anytime I'm doing a probability, I'm calculating all the chances that there is that this thing happens. So yes, I'm assuming that I did pick a king when I go to this next spot, or else why would it even be a part of what I'm calculating? Because I'm always looking at how many things match what I'm looking for. So sure, I could have picked any card in the first one, but there's a 4 to 50 chance that I get a king. Given that I got a king, there's a 3 to 51 I get another king. I like it. I don't know if anybody sees what we're talking about.
If the first card is not a king, then the
It
entire.
wouldn't even be included in this calculation anyway. It's not even in here.
The entire condition fails and.
It's not even in here. Yeah, so we're only looking at the situations that match this. Good question, though. That is a good question, even though nobody's got a follow-up. Good. It's a little bit freaky. All right. So try the rest of number 2.